In this chapter, we are going to learn about the properties and identities of trigonometric functions. So consider if we are given a problem which is cosecant x times with tangent x, and then that's equal to 3. So we are told to find what is the x value that can fit these equations. If we don't know about the properties or the identities, that will be a problem. But in this chapter, we learned that cosecant x actually is 1 over sine x, and then tangent x is actually, by the quotient properties, is sine x over cos x equal with 3. So we can have this will be 1 over cos x equal with 3. Then we can have also cos x equal with 1 over 3. So x will be equal with cos inverse of 3, which is around 1.231. All of this happened because we know the properties or the identities of the trigonometric functions. So let's start it. The first one will be the Pythagorean properties. I'm going to review again on sections 4.2. So I presented over here two figures. As you can see over here, the first one will be related to the sine functions, right? Because you have the inflection point at the origin, and then it goes to the high point, low point, and then it ends up on one cycle at 2 pi. So the second will be cosine, because it started with a high point and then it ended by 2 pi on the period of 2 pi at high point again. So this must be cos theta. Cos x, sine x and cos x. So I put it over here, the writings, sine x and cos x. Now, if we square sine x and cos x, what will it be? What I mean by squaring is this. If I put sine square x, which is sine x times with sine x, and then if I have cos square x, which is cos x times with cos x, then what will it be? Now try to imagine if you have like this negative area over here. When you square it, let's say you have -1, when you square it, it must be bounced to 1, and all of the negativity over here, when you have square, then it will be goes to positive. So I'll present you the picture. So this is it. You can have the blue graph over here. This represents the sine x. As you can see, the negative, it becomes positive because you have the multiplications with the negative again. So for cosine, it will be something like this, the green graph. Now what if I combine sine square x with cos square x? So if I combine these two, I'll have something like a double helix, but it's just like a shape of it. So you have the blue graph, I put it over here, the green graph, I put it over here, which is the cos square x. And when I combine it, let's say when I have the blue graph has a value of 0 and the green graph has a value of 1, when I add it, it becomes 1. So same thing on each value of this, then I can present that cos square x plus sine square x is equal to 1. So this is graphically proving that cos square x plus sine square x equal with 1, which means that if I put cos square 37 degree plus with sine square 37 degree, then on your calculator you always have that's equal to 1, or any kind of number which is same. Let's say 6 and 6 over here, and if we change it, then that will be equal to 1. So let's have some other properties. The first property that we are going to learn is, is the reciprocal properties. So let's rewrite again all things that we know about the trigonometric functions, those 6 trigonometric functions. So we have sine x, okay, in this case let's put sine a, cos a, cotangent a, secant a, and cosecant a. So we have sine a, in this case will be the opposite over hypotenuse, which is a over c. Cos a will be equal to b over c. Tangent a will be equal to a over b, and then cotangent a will be the reciprocal of it, which is b over a, and then secant a is c over b. So cosecant a will be equal with c over a. So then we can tell that tangent and cotangent is reciprocal, cosecant and secant is reciprocal to each other, and sine with cosecant will be reciprocal to each other. This property actually we are already learned, so I'll just give it like this. Sine x is equal to 1 over cosecant x, or you can also say cosecant x is equal with 1 over sine x. Not a new thing, right? If you have cos x equal with 1 over secant x, then secant x is also true to be said 1 over cos x. And then last one, if you have tangent x equal with 1 over cotangent x, then cotangent x is also equal with 1 over tangent x. So this is the reciprocal properties. The second will be the quotient properties. I'm going to rewrite it again for us. Sine a equal with a over c, the opposite over the hypotenuse. Cos a will be equal to the adjacent over the hypotenuse, and then tangent a will be equal to the opposite over the adjacent. Now I mentioned before in the previous lessons that tangent a is actually equal to sine a divided by cos a. Why? Because when you try to have tangent a, you can put it this way: tangent a equal with sine a over cos a, and cross check if the value is same, a over c over b over c. Apparently it is a over b, so that is the tangent, the proportions of the opposite length divided by the adjacent length. So if tangent a is equal with sine a over cos a, then we can also say that cotangent a will be equal to cos a over sine a. So this is the quotient properties. If we extend it by combining it with the reciprocal properties, we know that tangent a is also, so let's put it sine a over cos a. So cos a is the reciprocal of cosecant. So if I have cos a, I'll have 1 over secant a. So then I can also write that tangent a is also true to be said secant a over cosecant a. So this is also the reciprocal, the quotient properties. And then cotangent a will be equal to cosecant a over secant a by having these principles. This is quotient properties. Tangent a equal with sine a over cos a, and also equal with secant a over cosecant a. Cotangent a equal with cos a over sine a, also equal to cosecant a over secant a. To prove the Pythagorean properties, which is the third one, I'm going to present us this graphic, which is u and v Cartesian coordinate, not x and y, u and v Cartesian coordinate. And let's say we have a circle which has a radius of 1. So don't mind this scale, okay? So let's consider that this is equal to 1. If I have a terminal side, which is this red line, and it stops at, let's say, u comma v coordinate. The angle is theta, which then I can have the reference triangle over here. So if I try to express the coordinate of u and v in a different terms, like cos x and sin x, or cos theta and sin theta, then I can refer to the hypotenuse first. So if the radius is equal to 1, then this is also equal to 1 since it's a circle. So this is 1. If I put it cos theta or sin theta, and let's say that this is u, and then this one is v over here. So I can present that cos theta is equal to u over 1, and sin theta will be equal to the v over 1. So to make it simple, cos theta equal with u, and then sin theta equal with v. And then I can have that cos square theta plus with sin square theta equal to 1. How do I get this? From the Pythagorean properties. If I have this leg, which is a u length and v length, so I can present that it is u square plus with v square equal with 1. So if I change this and with cos theta and sin theta, I can have cos square theta plus sin square theta equal to 1. And this is the first properties, which is cos square theta plus sin square theta equal with 1. First of the Pythagorean properties. If I divide it by sin square theta, then I'll have cotangent square theta plus with 1. Okay, I forgot to put this sin square theta also over here, equal with cosecant square theta. So I'll have the second, which is cotangent square theta plus 1 equal with cosecant square theta. On the other hand, if I have a cos square theta plus sin square theta equal to 1, and I decided to divide it by cos square theta on both sides, then I will have, for the first term it will be 1 plus with tangent square theta equal with secant square theta. So we have 3 Pythagorean properties. So I'm going to write it back for us. That will be cos square theta plus sin square theta equal to 1. We have also this, which is cotangent square theta plus 1 equal with cosecant square theta. And then the last is 1 plus with tangent square theta equal with secant square theta. If we have this, we can modify it again. Let's say if you need cos square theta, then you can have cos square theta equal to 1 minus sin square theta. But this is still considered as a cos square theta plus sin square theta. Of course, if you need to modify it, then it will be something like this. So I present it again over here. The reciprocal properties is this one, and then this is the quotient identities. Forget to put over here, it's equal to secant theta over cos theta, and then cotangent theta is equal to cosecant theta over secant theta. And then we have the Pythagorean identities. So let's try this kind of problem. given that secant A over sin A minus sin A over cos A, and then we have to prove that it's equal to cotangent A. So proving means that you only look at one side, okay? You don't try to mix both sides, so only on the left side, and then you work it from here and then go to cotangent A. So based on what we know, secant A will be equal to 1 over cos A, but what we're going to do is to make the denominator equal, so I can write it as this, sin A times with cos A, and over here on the numerator I can have secant A, that will be times with cos A, minus with sin A times with sin A, so I'll have sin square A. Okay, and then I can have secant A times with cos A, so I can write it, secant A is 1 over cos A times with cos A minus sin square A over sin A times with cos A. So then 1 over cos A times with cos A, that will be equal to 1 minus sin square A over sin A times with cos A. So 1 minus sin square A, that will be equal to cos square A. Yeah, in this case that is theta, so I can change it as a cos square A over sin A times with cos A. And cos square A is cos A times with cos A over sin A times with cos A. Then we can have cos A over sin A, which is equal to cotangent A. So this is one of the practice to use the these three